Hello, welcome to Advanced Composites. Today is the fourth day of the ongoing, which is second week of this course. Yesterday we just finished our discussion on the number of elastic constants required for especially orthotropic material, and we found that the number of elastic constants which are required to characterize such materials is 9. And then we developed relationships between stresses and tensor strains for such materials, and we also developed relationships between stresses and engineering strains for such materials. What we will do today is we will discuss similar stress strain relationships for several other types of materials, and what we will start with is a material known as transversely isotropic. So, we are going to discuss transverse isotropy. Transverse isotropy. So, I will make a picture first. And this is a block of material, fibers are running in the direction of all these red lines, and if I look at it from one particular end, I see the ends of fibers, and that is pretty much it. And here this is my L axis, or you can also call it axis number 1. This is my second material axis, and this is my third material axis. So, now this material, if I cut a plane, if I cut a slab of this material like this, and then if I try to find its modulus in the 2 direction and 3 direction, it will be same, right. I mean that is how, because the material is oriented like this, and because of that in the 2-3 plane, in 2-3 plane, the material properties are same and direction independent, right. So, they are direction independent. So, that means this material is transversely isotropic in 2-3 plane. In 2-3 plane. Now, the stress strain relationships for an orthotropic material were this 1, 2, 3, tau 2, 3, 3, 1, 1, 2. And then we had these elastic constants in terms of C's. And we had a strain epsilon 1, epsilon 2, epsilon 3, gamma 2 3, gamma 3 1, and gamma 1 2. So, what are the elastic constants? It is C 1 1, 1 2, 1 3, 0 0 0, C 1 2, 2 2, 2 3, 0 0 0, 1 3, 2 3, 3 3, zeros, and then I have 3 zeros here in all the remaining rows, and then I have 4 4, 0 0, 0, 5 5, 0 0 0, 6 6. Okay. If this material is transversely isotropic in the 2-3 plane, then what are the relationships between different material constants? It means that if I pull this material in 2 direction or if I pull this material in 3 direction, its Young's modulus or not Young's modulus, elastic modulus should be same, which means C22 should be same as C33. This is one. Similarly, if I exert a shear stress on this in the 1-3 plane, 1-3 plane. So, this is 1 and 3, 1-3 plane or in 2-3 plane, then again the shear moduli will be same, and what that means is that C55 should be same as C44. This is based on the type of material we are talking about here. And similarly, the C12 and C13 reflect the Poisson effect. So, C12 is equal to C13. And finally, and we will not discuss the proof of this last component C66, this can be mathematically expressed as C22 minus C23 divided by 2. So, what does that mean? That instead of 9 independent elastic constants, we now have only 5 independent elastic constants, and the remaining 4 can be found from these 4 equations. So, a transversely isotropic material which is 3 dimensional, not very thin, which is 3 dimensional in nature, has 5 independent elastic constants. 5 independent elastic constants. This is important to understand. We will consider another class of materials, isotropic. And without going into detailed proof, isotropic materials have only 2 independent elastic constants. They have only 2 independent elastic constants. So, what are the further simplifications? C11 is equal to C22 is equal to C33. Okay. C12 is equal to C23 is equal to C31, and then C66 is equal to C22 minus C23 divided by 2, and this is equal to C44 is equal to C55. So, these are the mathematical relationships. So, you have only 2 independent elastic constants, okay. Only 2 independent. So, suppose you know only C11 and C12, then you can compute everything, okay. You can compute all the other remaining 7 constants. So, isotropic materials have only 2 elastic constants. The last case we will do is special orthotropy in plane stress state. So, special orthotropy plus plane stress condition. So, we have already talked about what is a special orthotropy. If it is material is especially orthotropic, it has 9 constants, but then on top of that we are saying that it also has plane stress condition. So, when there is plane stress condition, what does that mean? That stresses are acting only in one plane, okay. So, what does that mean? So, you will have only suppose sigma 1, sigma 2 and tau 1 2. All other stresses, sigma 1 3 is out of the 1 2 plane, sigma 2 3 is out of 1 2 plane, sigma 3 3 is again out of 1 2 plane. So, we have only stresses in a particular plane. Now, it could be 1 2 plane or 2 3 plane or 3 1 plane. So, in this case we are just considering 1 2 plane. So, if that is the case, then we say all other stresses are non-existent. So, these are non-zeros and other stresses sigma 2 equals sigma 3 equals tau 1 3 equals tau 2 3, these are zeros. Now, if that is the case, if tau 1 3 is 0, then tau 1 3 is equal to what? It is equal to C 5 5 times gamma 1 3, right. And if tau 1 3 is 0, then whatever the value of C 5 5 be, gamma 1 3 is going to be 0. So, it tells us that gamma 1 3 is equal to 0. So, C 5 5 we do not care whether we can find it out or not, okay, does not matter, we do not need it, because gamma 1 3 is 0 and tau 1 3 is 0. Similarly, gamma 2 3 is also 0, because tau 2 3 is 0, gamma 2 3 is also 0. Okay. So, we have 9 constants and that number of constants, because of that it just comes down to 7, because we do not need C 4 5 and C 4 4, but this number of constants it comes down further. So, again I mean if you do all the math in an organized way, essentially what you end up with is sigma 1, sigma 2 and tau 1 2, and that equals epsilon 1, epsilon 2, gamma 1 2 times. So, this is equal to this strain vector times a stiffness matrix, and this stiffness matrix we will call Q matrix, and I will define what are these values. Okay. So, this is the Q matrix, and what are these values? So, Q 1 1 is equal to C 1 1 minus C 1 3 square by C 3 3. So, if you do the mathematics by this, you will actually get these relations. Q 2 2 is equal to C 2 2 minus C 2 3 square by C 3 3, and then Q 1 2 is equal to C 1 2 minus C 1 3, C 2 3 by C 3 3, and Q 6 6 is equal to C 6 6. So, if there is a material which is especially orthotropic and in a plane stress situation, then we need only 4 constants. It may have more independent elastic constants, but we do not need other constants. We only need 4 elastic constants, and these are Q 1 1, Q 1 2, Q 2 2 and Q 6 6. These are the 4 elastic constants we need, and we can do the whole mathematics and mechanics of these materials correctly, if that is the case. It may have other materials like I discussed earlier. It may have C 5 5 and C 6 6, but because it is a plane stress situation, we do not need these. So, they are irrelevant to us. Instead of 9, we need only 4 constants, and these are these 4 Qs. Okay. So, this is the conclusion of our discussion for today. What we have discussed today are several types of materials. We showed that starting from a especially orthotropic material which has 9 constants, we showed that a material which is transversely isotropic, these number of independent elastic constant, it comes down to 5. If the number of if the material is isotropic in nature, then we know only 2 elastic constants. So, there are only 2 independent elastic constants, and if the material is thin and it is having a plane stress condition, if it is thin and it has a plane stress condition, then because the strains in shear strains in 3 and 1 directions are 0, and also because sigma or stress in the third direction is 0, because of this we need only 4 elastic constants, independent elastic constants, and we have defined those elastic constants in terms of the Q matrix. So, what we will do tomorrow is we will learn how to transform these stresses from the principal material axis system to any arbitrary axis system, and we will learn how to transform this, so that we can, if we have especially orthotropic material in the status of plane stress, then we should be able to predict the stresses and strains in the system as long as we know the Q matrix. So, that is what we will do tomorrow, and then till then have a great day. Thank you.